Hello again. We're going to be doing an example with an oblique asymptote. If you're familiar with hyperbolas, some people call them slant asymptotes. Actually, I call them slant asymptotes as well, pardon me, because I just think it's easier for students to remember, like it goes at a slant, so it's a slant asymptote. I guess oblique because, it's like your obliques, whatever, for those, like people at the gym, I'm building up my obliques. Anyways, that's going a little too far there. Pardon me. So we've got this function of x where it's equal to x squared minus 9 over 2x minus 4. And basically what we were talking about before was horizontal asymptotes. If the degree of the numerator, that is, like the exponent in the numerator of the highest term, or from ascending order to descending, was smaller than the denominator, then the horizontal asymptote was at 0. If they were the same, then what you do is you divide it by the degree, and then whatever your leading coefficients are, that's your horizontal asymptote. And if your degree of your numerator is bigger than the degree of your denominator, there is no horizontal asymptote, except, and there is a precaution here, if the degree of your numerator is 1 bigger than the degree of your denominator, so this is a 2 and this is a 1, then you have something called an oblique or a slant asymptote. And that's what we're going to talk about here. There is a slant asymptote to figure out. And there's a way to do it. And it's not by dividing by x squared like we do with the horizontal asymptote, because what we do is we get a undefined answer, and that doesn't answer anything for us. So instead what we do is we actually take this, we divide x squared minus 9, we take x squared minus 9 divided by 2x minus 4. And we have to do that. Now some people ask, well, how do I do that? Long division, anybody? That's usually the best way to go ahead and do it. So that's what we're going to do here. When I do long division though, I've got to account for every term, just as a placeholder. It's x squared minus 9. Well, put a 0x in between if there's no term in between the x squared and the 9, because you want to make sure that you're dividing everything correctly. And that's all divided by 2x subtracted by 4. Now, on a particular problem like this, I would have students that say, how do I do this one and this one? Like what times 2x equals x squared? I'm glad you asked. If you ever want to figure that out, you just take x squared, or you take this term and you divide it by the first term. And x squared over 2x is, let's see, x over 2, or 1x over 2, but it's just x over 2. I should do that in a different color. I don't want these to smear with each other. Pretend I already did that in green. So x squared over 2 times 2x is x times x is x squared, the 2's divide out, so I got x squared. X over 2 times negative 4 is negative 4x over 2, which is negative 2x. Change the signs. When you do regular long division without any variables, you do the same thing. You do it here too. Boom! That cancels. And I've got 2x subtracted by 9. Well, how many 2x's fit into 2x? The answer is 1. 1 times 2x is 2x. And 1 times negative 4 is negative 4. Change the signs, and you got something called a remainder, and your remainder is negative 5. So your answer when you take this one divided by this one is x over 2, let's make it 1x over 2, plus 1, remainder negative 5 over 2x minus 4. When we're finding the slant asymptote, all we do is we just disregard the remainder. So our slant asymptote is actually 1x over 2 plus 1. That's it. So I'm going to use this part of the board right now. 1x over 2 plus 1. We don't have a horizontal asymptote because we're not going to have a horizontal and a slant asymptote. We have a slant asymptote. Slant asymptote. You can call it an oblique if you want to. OA. Whatever. Now we're going to see if there's a vertical asymptote. Is there any value for x that will make the denominator equal to 0? And yeah, there is. 2x minus 4 equals 0, set it equals 0. So I'll do it anyways. 2x subtracted by 4 equals 0. Add 4 to both sides and then divide by 2. And what you get is 4 over 2, so it's at 2. Do you have an x and a y-intercept? Well, the answer is yes. And you got to figure out what those are. I think y-intercept is always much easier to figure out because you just set, you just set your x equal to 0. Bam. So disregard anything with an x. You got negative 9 over negative 4. That's 9/4. Or it's like 2.25. We're just going to make it 9/4 now. 2.25, yeah, 2.25, 9/4. If you want to figure out your x-intercept, set your y equal to 0. Okay, so 0 equals this. Cross multiply, so 0, you know, when you cross multiply 0 and this, it's still 0. So 0 equals x squared minus 9. Okay, I guess I'll do it here. 0 equals x squared minus 9. The easier way to do it in this case, you could factor, actually, that's pretty cool. But all you really have to do is just add 9 to both sides. So it'd be 9 equals, I sure hope you can see that, 9 equals x squared. And then take the square root of both sides. And when you take the square root of both sides, what you get is 2 x-intercepts. One is at 3, and the other is at here. I'm going to circle that. I don't want it to be confused with a point. And the other is at -3. And there you go. So I guess I'll draw a really quick graph about this since I've already done this anyways. What's really interesting is that your slant asymptote is at 1x over 2 plus 1. So basically it's at a line. So when I graph that, you've got a slant asymptote like this. So your graph will never actually, you know, like kind of cross that. That's what's really cool about it. So when your graph extends to infinity, it's gonna, you know, either fold like this or fold like this, or maybe it'll fold both ways. But that's really cool. See, that's what a slant asymptote means. You know, like as I go to negative infinity, it's gonna hug this line. My vertical asymptote is at 2. So I'm basically partitioning my graph. And then the other thing to keep in mind is that I have an x-intercept at 3 and at -3. So here's one at 3. Here's, I don't even know what this is. Down 1 over 2. Let's see, well technically that's at 2, so here, that's -3. If I drew my graph correct, if I drew my slant asymptote correctly, I would not have had that problem, but you know, hindsight's 20/20. My y-intercept is at 9/4, which is like 2.25, so it's like here. So that's all I really have to work with. I know I have points on a graph that exist here, I know I have a point on a graph that exists here. I know that my graph has to either extend this way or this way, and it has to extend this way. So, you know, if I was going to do a really quick graph, I'd say, okay, yeah, one of them looks like this, because I know that it's going this way, and it's going this way, because that's what my vertical asymptotes basically do. Well, my asymptotes in general, they guide my graph. And then I say, okay, I got a point here, and I got a point here, and the graph goes up like this, and it goes like this, so I'm thinking that, oops, probably hugs that line. That was a very terrible way to draw this graph. Let me do that again. Yeah, maybe that's better. Who can ever tell? I don't know if it's actually perfect because I didn't sit there and, you know, put an XY table. But just with this information right here, I was able to basically be able to ascertain the shape of the graph, which is really cool. It's a lost art. You know, when you do horizontal or oblique, you know, you have students who just come out and just, you know, plug it into the calculator. And I guess there's nothing wrong with that either. I mean, if I had a choice of taking like a minute to solve a problem or 10 minutes, I'd solve it in a minute too. But the thing is that I learned how to do this before I tried learning it into a calculator. And I think that's very important, but, you know, if math isn't your thing and you just want to just kind of get by, I understand that too. With that said, I hope it was helpful. Have a good day for now. Goodbye.